Hello students, welcome to EPG Pathsala. I am Sunil Kumar from IIT Delhi. Today we are going to discuss about a module on fluids, properties of fluids at rest and properties of fluids in motion. For example, the laminar flow, the turbulent flow and Bernoullis Principle, etc. So the basic thing that we try to learn in this module is to learn about the properties of fluids at rest and the properties of fluids when it is in motion. So we will learn about the following topics. Obviously, what is the basic definition of fluids? We will start with that, and some properties, basic properties which are always referred to when you discuss about fluids. We will discuss about surface tension and capillary effect, which is always studied in the cases of liquids, water or oil, etc. Then we will discuss Pascal's law, we will discuss Archimedes principle, we will discuss viscosity, what are highly viscous liquids and what are low viscous liquids. We will learn about the flow of fluids, laminar flow, which is flow along a specified geometry. We will learn about turbulent motion of fluids. Then we will discuss continuity equation, which is again for the fluids in motion. And then we will learn about Bernoulli's theorem, which has various applications. So to start with, the basic definition of a fluid. Anything that can flow is termed as fluid. Okay, so it means not only the water that we drink is fluid, but the gases around you, that also is fluid. The two basic properties which are always referred to while discussing fluids are density and pressure. So density is mass per unit volume and pressure is force per unit area. So these two basic properties are always referred to when you want to discuss the properties of fluids. Basic description of surface tension can be understood from this picture, where you have a liquid in a container. The net force on a molecule inside the liquid, the fluid, is non-zero, while that on the surface is non-zero. The unbalanced net force on the molecules on the surface causes the outer layer of the liquid to act like a stressed membrane, which tries to minimize its surface area. This elastic membrane-like behavior of the liquid is the surface tension. Mathematically, it is the force per unit length along the surface, and the dimensions are Newton per meter. The examples which you come across, which can nicely explain the surface tension, or you can understand it, are such as a water drop at the tip of an object or a rod which is just about to leave the tip. So why there is a shape, why the water drop is having a shape of that sort. In the second one, you must have seen water drops on a smooth surface or water drops on leaves. So why these are like this? Why you see the water drops like that? It's all because of the surface tension of the liquid, or in these cases of water. So you will see water drops or you won't see them. It all depends on the contact angle between the liquid and the surface. For liquids on a non-wettable surface, the contact angle is smaller than 90 degree, and therefore the surface tension dominates the attractive forces on the surface. In the other case, for liquids on a wettable surface, the contact angle is going to be larger than 90 degree. In that case, the attractive forces to surface exceed the surface tension and you don't have drop like water on the surface. So the contact angle which we are talking about here is basically the angle between the surface and the surface of the water drop or water or liquid, any liquid. So due to this surface tension of liquids, you see many interesting phenomena. The first one or one of them is meniscus. What is meniscus? It is due to the cohesive and adhesive forces between liquids in contact with some solid surfaces. For example, adhesive forces, due to adhesive forces, the liquid level climbs up, and for cohesive forces, it drops down. Adhesive forces are, for example, between water and glass tube, and cohesive forces, for example, are between mercury, which is kind of semi-fluid, and glass tube. In the first case where you have water and glass tube, because of surface tension and the adhesive forces between glass and the water, you have water climbing up the tube. In the second one, due to cohesive forces, the mercury level drops down in the glass tube. So capillarity. So capillarity is a property of the fluid in combination with, for example, here glass tubes, that because of the surface tension, the level of rise of the fluid in glass tubes is different depending on the size of the tube. So due to surface tension, liquids rise or drop to different levels in thick and thin glass tubes. And the height of the liquid is such that its weight is balanced by the surface tension. In the picture here, we have three glass tubes of different diameters. You pour certain liquid or water, let's say, here. So depending on the diameter, you will have the water rise into different heights, such that the water in all three tubes has equal weight because it has to balance the surface tension of the water. Another static property of fluids is or can be seen through Pascal's law, which is for any fluid in an enclosed system, and it states that a change in pressure at one point in the fluid is transmitted to all other points in the fluid. For example, in this picture, you have the enclosed system of liquid and there are two pistons at the two ends of the container. In one piston, you have a force applied F1 on an area A1. Because of this force per unit area, you have a pressure developed in the fluid. So because of the Pascal's law, at every point inside the fluid, the pressure has to remain same. That means at the other end, where there is a piston, the force gets transferred or the pressure gets transferred, and because the pressure is force per unit area, you have a net force on the piston at that end, because of which the piston gets lifted up. So naively you can now think of many examples where this Pascal's law is applicable. One of those examples can be hydraulic machines, such as the garbage trucks, the hydraulic lifts, and so on. In all such examples, the Pascal's law is operational, and in these examples you have, because of the pressure developed in the fluid, that is made useful for various purposes. For example, lifting a truck, or for example in hydraulic scissors, which is acting as a lift table, and so on. Let's understand Archimedes' principle. The principle says that any body completely or partially submerged in a fluid, either gas or liquid, the fluid has to be rest. So the body is acted upon by an upward force that is called the buoyant force, whose magnitude is equal to the weight of the fluid displaced by the body. Mathematically, what it means is the apparent weight of that body, which is floating or floating in the water or in liquid, in fluids, is equal to the actual weight of the body minus the magnitude of buoyant force. Take an example of a wooden block floating in water. So if it is inside the water, the two forces, if it is floating inside the water, the two forces have to be balanced. What are the two forces? The first one is its weight, which is actually m into g. M is the mass and g is the gravitational constant or gravitational acceleration. So the mass is basically the density into volume. That is the weight, that is the first force which is acting downwards on the block. If it is floating inside the fluid, it means the buoyant force also has to be equal to the weight. So in that case, if the block is inside the water, you can see that the density of the block and the density of the water have to match. On the other hand, if the block is floating on the surface of the water, meaning that you have some part of the block inside the water or inside the fluid and some part of the block outside the fluid. In that case, the water displaced by the block, the volume of the water or the fluid displaced by the block is much smaller than the volume of the block itself. So in that case, if you compare these two forces, the first force is the weight of the block and the second force is the buoyant force, there is clearly a difference between the densities of the block and the water. So if the two densities are different, okay, then either the block is floating on the surface. If the two densities are same, the block is floating inside the fluid, and if the density of the block is larger than the density of the fluid, then the body is not going to float. It will simply go to the bottom of the fluid of that container. So the concept that we learn in that when the objects float in a fluid and when they drop down, or whether they float on the surface of the liquid, it all depends between the differences in the density of the object and the liquid in which you are trying to make the object float. So depending on the weight of the object and the weight of the fluid displaced by the object, whether it is smaller or equal or larger, the object can float on the surface of the fluid, or it can simply go to the bottom, or it can float inside the fluid. It all depends what is the difference between the two weights or the two forces, which eventually comes out to be the difference between the density of the object and the density of the water. Now let's discuss about the properties of fluids in motion. So in the beginning itself, it has to be made very clear that the fluid dynamics means study of fluids in motion. So the fluid dynamics is not really very easy, it's quite challenging and it's quite complex. So the way we learn about fluids at rest, those properties of the fluids can be very easily understood. But when the fluids are in motion, there are so many other factors which have to be taken into account before we can really describe the fluids completely. Meaning that the properties of the fluids are not very obvious. So when we want to understand the dynamics of fluids, we have to make some approximations. So the first approximation is about the fluid itself. We assume that the fluids are ideal, and then we study their flow dynamics. So what are the properties of ideal fluids? Ideal fluids are those fluids which have steady flow, meaning that the velocity of a specific fluid component does not change randomly, does not change abruptly. Second property of the ideal fluids is incompressible flow. The flow should be incompressible. Third property that makes the fluids ideal is that the flow has to be irrotational. And the fourth one is that the flow has to be non-viscous. So any fluid which satisfies, or to study the dynamics of fluids, we have to assume these four conditions in the beginning itself and then study the dynamics of the fluids. You have this picture in front of you here. In this picture, what is described is the streamlined flow of fluids. What is streamlined flow? Is any component of the fluid. Here it is represented by dot. If it has a velocity v, it maintains that velocity at each point, number one. Number two, it follows a trajectory which is very well defined. So then this flow actually becomes streamlined flow. So more accurately, the steady or laminar flow is one in which the velocity of moving fluid at any fixed point does not change with time. Pictorially it is shown here. So straight arrows means that the velocity, if you can represent the velocity of the fluid component by these arrows, so straight arrows means the velocity remains, or the speed of that fluid component remains constant all the time when it is moving in a well specified path or geometry. On the other hand, in the case of turbulent flow, the fluid of liquid component or fluid component at a fixed point cannot be specified properly. So here you cannot represent the velocity of fluid component by straight arrows the way you did it for laminar flow. In this example here, you have flow of particles rising in a stream of smoke. So at bottom end, you have the speed of the particles in the streamline, whereas as you go away from that point, you have turbulent motion of the particles, because as you move away from the bottom part, the particles become more random in terms of their velocities, and they no more remain moving on specified paths or curves. So for an understanding, it is easy to simulate the linear dynamics of laminar flow. However, nonlinear dynamics of the turbulent flow is quite complex to simulate on a computer. So you might have seen various examples of laminar flow in your life. In laboratories, we have laminar flow hoods. What they do is, you have flow of gas from top to bottom or from one side to the other in a laminar way, meaning that with that laminar flow of the gas, the dust particles or the gas molecules, unwanted gas molecules, are dragged with it from one direction, from one end to the other end, and that's how you keep the environment inside the hood clean or healthy for the person who is working with chemicals. Let's now come to viscosity. It is an amount of internal friction between various layers in the fluid, due to which a test particle experiences a particular drag force opposite to the direction of the fluid flow. Mathematically, the expression for the drag force is given as F equals eta, which is the viscosity coefficient, times A times V times L. A is the area of the fluid in contact with the fixed surface, V is the velocity of the fluid, L is the perpendicular distance from the surface, and eta, as I said, is the coefficient of viscosity. So you can see from this picture that as you go away from the fixed surface, the velocity of the fluid keeps on increasing linearly, and the drag force, because the eta is constant, and L, as you go away from the fixed surface, L increases, so the drag force F also keeps on increasing. In this slide, we see, depending on the value of the viscosity coefficient, various kinds of viscous fluids. So every fluid is viscous, it just depends on the degree of or the magnitude of the viscosity coefficient. The low viscosity fluids, the examples can be gas, liquid helium, spirit, and so on. Some examples of medium value of or mediocre value of the coefficient of viscosity can be water. Other examples of highly viscous fluids can be like honey, fruit jam, oil, curd, paint, and so on. So in this animation here, what you have is, in the top part, you have a fluid which flows quickly. It's kind of thin as well. So it has got smaller coefficient of viscosity, and in the lower part of the animation, you have a fluid which flows very slowly. So it means it has much larger value of the coefficient of viscosity. So immediately from this animation, you can imagine about the differences between gas or liquid, water, and the honey, oil, paint, and so on, and see which fluid has got smaller or higher coefficient of viscosity. So due to viscosity of the fluids, any particle moving through that fluid experiences a drag force, and the amount of the drag force is directly proportional to the velocity of that particle. Higher the velocity of the particle, higher is the amount of the drag force. The drag force is characterized by Reynolds number. For laminar flow, the magnitude of the value of the Reynolds number is smaller than 1. For aerodynamic objects, Reynolds number being lesser than 1 ensures that the wind resistance is minimal. So in the concept of drag force, now we will describe two important things. The first one is the Stokes equation, which is for spherical objects. The second one is terminal velocity. So Stokes equation describes the drag force on a spherical object which is moving through air or through fluids under gravity. So in this picture you have the object with velocity v moving down towards Earth with the gravitational force Fg acting on it, has got density rho m as compared to rho a for the fluid or air. Because this is the motion of the object in a fluid, so there is a buoyant force which is opposite to the direction of the motion, and then there is this drag force because of the flow of the fluid as well. So as a resultant force on the object is towards the ground. For this object, the drag force is given by 6 pi times the viscosity of the fluid times the radius of the object times the velocity. So at any point where the velocity of the object is given, we can estimate at that point how much drag force is acting on the object. This equation is valid only for spherical objects and is known as Stokes equation. So if the forces are balanced, then the object attains a constant velocity towards the ground, that is called terminal velocity, and it is simply given by this expression, which again depends on the viscosity of the fluid and the difference between the density of the object and the fluid, and nothing more. Another important concept in the fluid dynamics is equation of continuity. It says that the rate of flow of a fluid through a cross section per unit volume or per unit time is always constant. For example, in this picture here you have a container through which the fluid is flowing. At one end the cross sectional area is A1, and on the other end, which is narrower than the previous one, the cross sectional area is E2. So because of the equation of continuity, the fluid flowing through cross section A1 is A1 times V1. V1 is the velocity of the fluid at that point, has to be the same as the fluid flowing through the other end, the narrower end. And the rate of flow at that end is A2 times V2, where V2 is the velocity of the fluid at that end. So the equation of continuity sometimes is very useful in finding out the velocity at an arbitrary point inside the fluid or inside the container through which the fluid is flowing, depending on the geometry or the size or the cross section of the fluid at that point. We can estimate whether the fluid is going to have higher or smaller velocity as compared to any other point, or at a point where the velocity is known. As an example of equation of continuity, here you have two blood vessels. In the first one, the upper one, you have normal amount of blood flowing through the blood vessel, and because of that you have normal blood pressure. Sometimes these blood vessels get narrower, and when they get narrower, because the blood pressure has to remain constant everywhere inside the body, what you are going to have is, because of the narrower of the blood vessel, you have high blood pressure in those regions where the blood vessels have got narrower as compared to those regions where they have got normal size. Here we have three examples just to calculate, just to get a feeling about the differences in the blood pressure. In the first one, you have very narrow blood vessel with radius of 0.95 in some units. There you have got the blood flow as 0.8145 milliliter per minute. If the size of the blood vessel or the radius of the blood vessel goes to 1, then you have got increased blood flow, and when you double the radius again, you have the blood flow which gets increased by 16 times. So here we have the r to the power 4 factor involved, which can be easily seen through this example from where this r to the power 4 factor is coming. That is coming from the equation of continuity, that at each point you have cross section area times the velocity equals constant. Bernoulli's theorem is an important concept in the fluid dynamics. What it says that the net energy of the fluid in motion is same everywhere, meaning at every point inside the fluid flowing through a container or tube or on some surface, the net energy of the fluid remains the same. So what kinds of energies the fluid can have when it is flowing through on some surface or through some tube or container? It has the pressure energy plus the kinetic energy plus the potential energy. The sum of all these energies has to remain constant throughout the whole fluid. If at some points you have smaller kinetic energy because of smaller velocity of the fluid component, then there is a change either in the pressure energy or the potential energy, and so on. So what we learned from Bernoulli's theorem is that from various points to points inside a fluid, the total energy has to remain constant, which helps us in finding out at points what can be the velocity of a fluid component, or at a given point or given height what will be the velocity of that fluid component. As an example of Bernoullis principle, we have air pressure difference between airflow above and below the wings of an aeroplane helps it take off. This is explained through this cartoon here. So you have airflow from the forward direction, and because of the curvature or the shape, the way the wings of an aeroplane are designed, they create a pressure difference between the air flowing above and below the wings, and that pressure difference is such that you get an upward thrust. That upward thrust helps the plane to take off. Now let's go through a couple of sample problems which are based on the knowledge that we have got from this module. In the first sample problem, we have a smaller piston of a hydraulic lift that has radius of 5 cm and that of the large one has radius of 50 cm. If 8.8 Newton force is applied onto the larger piston, what would be the maximum weight that can be lifted at the smaller piston? So if you do it using the concepts that we learned in this module, then you would get the answer of 88 newtons. In the sample problem, Archimedes principle has to be used. So 3 blocks of equal volume are completely submerged into water. The blocks are made of aluminium, iron and lead. So you have to compare the buoyant force on each block. What is given here is the material densities. In case of aluminium, it is 2700 kg per meter cube. For iron, it is 7800 kg per meter cube. And for the lead, it is 11,300 kg per meter cube. So immediately from the difference in the densities, you can guess or you can estimate, you can anticipate what kind of forces you will get, what kind of buoyant force you will get on these blocks, and whether, because you have to compare the density of these materials with the density of the water and see if that difference can allow the blocks to float in water or not. Let's summarize the module now. So we learned that density and pressure are the main properties which differentiate fluids from solids. We learned that fluids are not only the liquids but gases also are a form of fluids because they flow. We learned about Archimedes principle, which says that the weight of floating objects and the fluid displaced by them have to be the same. Thirdly, we learned about laminar flow, which means the velocity of fluid components inside the fluid at any point has to remain the same. Then we learned about viscosity, which is a property of fluid that determines the resistance felt by any object flowing through the fluid. Then we discussed about equation of continuity, which states that the rate of flow of a fluid is constant throughout the flow. And then finally we learn about Bernoullis principle, which states that in laminar flow, the energy density at every point in the flow in the fluid remains constant. Thank you.